All right, so today we're taking a deep dive into an OEIS sequence that I think is going to be really intriguing, especially for anyone out there who's into number theory. You ready for this?
Always ready for a good sequence. What we got?
All right, so it's A001168. And like I said, this one's going to be particularly interesting for number theory folks because it's all about these things called rooted planar maps.
Oh, rooted planar maps. Classic. Those are always fun to think about. They're surprisingly deep, you know?
Yeah, and that's what I think is so cool about this sequence because, like, at first glance, it seems pretty simple. AN counts how many rooted planar maps you can make with exactly n edges.
Right.
Pretty straightforward.
Straightforward concept. And it even has this really nice formula. AN equals 2 times 3 to the n times 2n factorial, all divided by n factorial times n plus 2 factorial.
Yeah, exactly. Which, that formula itself is kind of a giveaway that there's something more going on here, right? Like all those factorials, come on, that's not an accident. It's hinting at some deeper structure, some way these maps are built up.
Absolutely. Factorials usually scream combinatorics, and in this case, they're telling us there's a story about how these maps are put together, piece by piece, from simpler elements.
And it's not just the formula that's intriguing. What's really wild is how this sequence shows up in all these seemingly unrelated places. Like you see it with 4 regular planar maps. You see it with these crazy self-intersecting curves they call doodles, where it counts how many doodles you can make within crossings.
Don't forget lambda calculus.
Oh, yeah, lambda calculus, too. Specifically, it has something to do with the shapes of those closed normal linear lambda terms. And then there's well-labeled trees. Like, how are all these things connected to counting maps on a surface?
Right. It's a real testament to the interconnectedness of mathematics, how one simple sequence can be like a bridge between these different worlds. And it's not just random connections either. There's this mathematician, Noam Zeilberger, who's done some fantastic work showing how A001168 fits into this whole network of related sequences.
Oh, really? What kind of sequences are we talking about here?
Well, there are sequences related to planar maps, obviously, but also things like the Tamari lattice and lambda calculus, as I mentioned. We're talking about A000260, A00000698, 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 A006298, even 867,827. It's really remarkable, this whole web of interconnectedness he's uncovered.
Wow, that's a lot of connections. I have to check those out. And then on top of all that, the OEIS also mentions this integral representation for the sequence, which is kind of blowing my mind. It says it's the nth moment of some positive function. I mean, what does that even mean in this context? Like, we're counting maps and suddenly we're talking about integrals and analysis.
Right. It's a bit of a jump, but it's actually a really powerful clue. When you see a combinatorial sequence popping up as the moments of a probability distribution, it often means there's some deeper analytical structure going on, some connection to random processes maybe.
Huh. So, like, maybe the way these rooted planar maps grow and behave is governed by similar principles that show up in, like, continuous phenomena?
Exactly. That's the kind of thing that mathematicians get really excited about, these unexpected connections between seemingly different areas.
Okay, so clearly there's a lot to unpack here. But before we get too deep into the weeds, let's just back up and make sure everyone's on the same page. What exactly are we talking about when we say rooted planar map?
Right, good point. So let's start with planar graph. A planar graph is just any graph that you can draw on a flat surface, like a piece of paper, without any of the edges crossing each other. Simple enough, right?
Yeah, I think everyone's familiar with the idea of a graph and drawing it without crossings.
Good. Now, a plane graph is just one specific way to draw a planar graph without those crossings. But here's where it gets interesting. A planar map takes that idea and moves it onto the surface of a sphere.
Onto a sphere, huh? Okay, I'm following.
Basically, think of it like this. You have your planar graph, and you can imagine drawing it on a flexible sheet. Now, wrap that sheet around a sphere, and boom, you've got yourself a planar map.
So it's like taking the graph and sort of inflating it onto a sphere, but without letting any of the edges cross.
Exactly. And the key difference here is that in a planar map, there's no special outside region like you have on a flat piece of paper. Every face of the map is treated equally.
Okay, I see. It's about the graph's structure on the sphere itself, not a particular drawing on a flat surface with some arbitrary outer face.
Gotcha. But what about rooted? The OEIS description mentions rooted planar maps with n edges.
Ah, yes, rooted. That's a crucial detail. Rooting a map essentially means you pick one special edge and give it a direction, like an arrow.
And why do we do that? What's the point of picking that special edge?
It's all about avoiding double counting. See, without a root, you could rotate or flip the map around and it would still be the same map, just in a different orientation. But by rooting it, you're fixing a specific reference point. So any two maps that look the same after you rotate or flip them are considered the same map if they also have the same root. Oh, I see. So it's like marking a starting point on a map so you don't get lost. It helps us define exactly what we're counting.
Precisely. And remember, we're focusing on maps with a specific number of edges, not necessarily vertices.
Right, that's important. So we've got our rooted planar maps defined. Now let's go back to that formula. AN equals 2 times 3 to the n times 2n factorial, all divided by n factorial times n plus 2 factorial. How do we even begin to make sense of that?
Well, the first thing that jumps out at a combinatorialist like myself is the presence of those Catalan numbers lurking in there.
Catalan numbers, those are those things that pop up everywhere in combinatorics, right?
Exactly. They count all sorts of things. Binary trees, Dick paths, triangulations of polygons, you name it. And in this formula, you can see them if you rearrange it a bit.
So how does that work?
Well, you can rewrite the formula as AN equals 2 times 3 to the n times Cn, all over n plus 2, where Cn represents the nth Catalan number, which is 1 over n plus 1 times 2n, choose n.
So the Catalan numbers are like a hidden ingredient in this formula. What does that tell us?
It hints at a deeper connection. It suggests that there might be a way to build rooted planar maps using these other Catalan-related structures. Maybe there's a step-by-step process, or maybe we can decompose a map into pieces that are counted by Catalan numbers. It's like a breadcrumb trail leading us to a hidden relationship.
Wow, that's pretty cool. So this sequence isn't just some isolated thing. It's connected to this whole world of Catalan objects. And what about that asymptotic formula we saw in the OEIS, the one that goes AN, is roughly equal to 2 times 12 to the n, all divided by this whole mess of n squared plus 3n times the square root of pi times n. What does that tell us?
That formula tells us about how fast the number of rooted planar maps grows as the number of edges gets bigger. The key part is that 12 to the n, which means that the number of maps explodes exponentially as n increases.
So, like, the more edges we add, the more possibilities we have, and the number of maps just goes crazy.
Precisely. It's a bit like compound interest. The more you have, the faster it grows. And those other terms in the denominator, the n squared and square root stuff, they give us more precise information about how that growth is shaped.
Okay, so the formula tells us these maps multiply like rabbits. But the OEIS also mentions some other really unexpected connections. Like, it says, this sequence counts rooted 4 regular planar maps with n vertices. Can you remind me what a 4 regular graph is again?
Sure. A 4 regular graph is just a graph where every single vertex has exactly 4 edges connected to it.
Okay, 4 edges per vertex. Got it. But what does that have to do with our rooted planar maps with n edges?
It all comes down to this really cool concept called duality. Imagine you have a planar map drawn on a sphere. Now, picture putting a dot in each face of that map. Those dots become the vertices of a new graph, which we call the dual graph.
Okay, I'm visualizing that. So each face of the original map gets a dot, which becomes a vertex in the dual graph.
Exactly. Now, if 2 faces in the original map share an edge, we draw an edge between their corresponding dots in the dual graph.
So the edges in the dual graph basically cut across the edges in the original map. Huh, that's neat.
It is. And the really cool thing is that the dual of a planar map is also a planar map. But here's the kicker. If the original map has n edges, then the dual map has n vertices, and it turns out to be 4 regular.
Whoa, that's wild. So by counting rooted planar maps with n edges, we're also indirectly counting rooted 4 regular planar maps with n vertices.
Precisely. They're 2 sides of the same coin, linked by this concept of duality.
That's amazing. And then there are those doodles the OEIS mention. What are those, and how do they fit into all of this?
Doodles. Those are fun. Imagine taking a pen and just drawing a continuous closed curve on a piece of paper, but you're allowed to cross over your own lines as much as you want.
So just a messy scribble, basically.
Yeah, kind of. But the cool thing is that we can count how many times the curve crosses itself, and we call those crossings. And what's really surprising is that the number of doodles with exactly n crossings is also given by our sequence, AI.
What? That's insane. So there's some hidden connection between drawing these doodles and counting rooted planar maps.
There is. It's like there's a secret code that translates between these 2 seemingly different worlds.
Yeah.
The exact relationship is still a bit of a mystery, but it suggests that there might be a way to think about planar maps as these kinds of self-intersecting curves.
It's like those magic eye pictures where you have to look at it just right to see the hidden image. Okay, and then there's the connection to lambda calculus. That's where things get a bit more abstract for me.
Lambda calculus is this formal system used in mathematical logic and computer science for expressing computation. It's all about functions and their application.
Okay, so it's a way of describing how calculations work.
Yeah, sort of. Now, there's a specific kind of lambda calculus called linear lambda calculus, where you can only use each variable once. And it turns out that the sequence AN counts the number of different ways to construct certain types of expressions in this linear lambda calculus.
Wow, so counting maps on a sphere is somehow related to the very foundations of computation. That's mind-blowing.
It is, isn't it? It really highlights how interconnected these seemingly disparate areas of mathematics can be.
Absolutely. And finally, there's the connection to well-labeled trees. What are those, and how do they relate to our rooted planar maps?
A well-labeled tree is basically a rooted tree where every node has a label, usually a number, and the labels increase as you move further down the tree.
Okay, so like a family tree where each generation gets a higher number.
Yeah, kind of like that. And the cool thing is, AN also counts the number of certain types of well-labeled trees. What this tells us is that there's likely a way to convert a rooted planar map into a well-labeled tree and vice versa without losing any information. It's like translating a sentence from one language to another, but with mathematical objects.
So, one sequence, so many different interpretations. It's like a mathematical Rosetta Stone. Okay, now let's delve a little deeper into the mathematical properties of this sequence. The OEIS mentions this thing called a generating function, AZ, which apparently satisfies a quadratic equation.
Generating functions. They're a powerful tool for studying sequences. Basically, you take each term in the sequence and stick it into a power series where the exponent of z matches the position of the term in the sequence.
So it's like encoding the entire sequence into a single function.
Exactly. And the cool thing is that the properties of that function can tell us a lot about the sequence itself. In this case, the fact that the generating function satisfies a quadratic equation tells us that the sequence has a nice recursive structure.
Recursive, meaning we can calculate later terms in the sequence based on earlier ones.
Exactly. And by solving that quadratic equation, we can get an explicit formula for the generating function, which can reveal even more about the sequence.
That's really neat. And the OEIS also mentions another form of the generating function, one that involves these things called hypergeometric functions.
Hypergeometric functions are a whole other beast. They're like the Swiss Army knives of functions. They show up all over mathematics. Seeing one here suggests that our sequence has connections to a very rich and well-developed area of analysis.
Okay, so things are getting pretty high level now, but the OEIS also gives us a more down-to-earth recurrence relation. N plus 1 times AN equals 12N minus 18 times AN minus 1. How does this one help us?
That recurrence relation gives us a practical way to calculate the terms of the sequence. You start with the first few terms, and then you can just plug them into the formula to get the next one, and so on.
So it's like a recipe for generating the sequence.
Exactly. And the fact that it's a simple linear recurrence relation makes it pretty easy to work with.
And then, just when I thought we'd covered all the bases, the OEIS throws another curveball, an exponential generating function with Bessel functions.
Bessel functions. Those are another fascinating class of special functions. They often pop up when you're dealing with things that have cylindrical symmetry or in certain types of wave propagation problems.
So what are they doing here in a sequence about planar maps?
That's a great question, and honestly, it's not entirely clear. But it hints at a connection between the discrete world of counting maps and the continuous world of analysis and differential equations.
So, yet again, we see these unexpected bridges between different areas of math. And then finally, there are these summation formulas provided by someone named Amiram Eldar, which involve inverse trigonometric and hyperbolic functions. I mean, what are those doing in here?
Those formulas are pretty wild. They provide these explicit connections between our counting sequence and these continuous functions from calculus. It's a bit like finding a hidden tunnel between two seemingly separate buildings.
Okay, so we've explored a lot of ground here, but before we wrap up, let's circle back to the foundation of all of this, planar graphs.
Planar graphs are indeed the building blocks of our rooted planar maps. And one of the key things to remember about them is Kuratowski's theorem. This theorem tells us that a graph is planar meaning you can draw it on a plane without crossings if and only if it doesn't contain a subgraph that's a subdivision of K5 or K33.
K5 and K33, what are those?
Think of K5 as the complete graph with 5 vertices, where every vertex is connected to every other vertex. And K33 is a complete bipartite graph, with 3 vertices on one side and 3 vertices on the other, and every vertex on one side is connected to every vertex on the other side.
Okay, so those are like the forbidden configurations that prevent a graph from being planar. Got it. What else is important about planar graphs?
Well, there's this really elegant formula called Euler's formula, which connects the number of vertices, edges, and faces of a planar graph.
Euler's formula? That rings a bell.
It states that for any connected planar graph, the number of vertices minus the number of edges plus the number of faces always equals 2.
Wow, that's such a simple and elegant formula.
It really is. And it's a fundamental tool for understanding planar graphs and their properties. Now, you might be wondering how the enumeration of all planar graphs compares to the specific case of rooted planar maps that we've been discussing.
Yeah, that's a good question. Is it easier or harder to count all planar graphs?
Counting all planar graphs is actually a much harder problem. While there are formulas that describe how the number of planar graphs grows as the number of vertices increases, there's no nice closed-form expression like we have for n. Our focus on rooted planar maps with a fixed number of edges makes the counting problem much more manageable.
So by adding some structure with the root and focusing on edges, we've simplified the problem and unlocked this whole world of connections.
Exactly.
And finally, let's touch on the broader concept of rooted graphs in graph theory. What does it mean to root a graph in general?
Rooting a graph is basically just picking one special vertex and calling it the root. It's like marking a starting point on a map. This idea is used all over graph theory, particularly in algorithms and network analysis, where you might want to study how things flow or spread from a particular point.
So it's a way of adding a reference point to the graph, which can be useful for all sorts of things.
Exactly. And as we've seen with our sequence, A001168, even just adding a root to a planar map opens up this whole world of fascinating connections and properties.
It's amazing how something that seems so simple can lead to such deep mathematical insights. So to sum up, OEIS sequence A001168 gives us a precise count of rooted planar maps with n edges, but it's so much more than that. It's a gateway to this incredibly rich and interconnected world of mathematical ideas.
I couldn't agree more. From its connections to Catalan numbers to its appearances in topology, lambda calculus, and analysis, this sequence is a shining example of the beauty and unity of mathematics.
And for our number theory friends out there, this deep dive hopefully shows you how even seemingly abstract combinatorial objects like rooted planar maps can have surprising relevance and potentially offer new tools or perspectives for your own research.
Exactly. Don't underestimate the power of combinatorics and its connections to other areas. You never know where it might lead you.
Well said. We encourage everyone to explore the OEIS further and dig into the references we've mentioned. There's a whole universe of mathematical wonders waiting to be discovered.
Happy exploring.
And thanks for joining us on this deep dive.